See here, you hold it, you look through the telescope, you need to aim it at the horizon and work with the stars to get an angle. Next slide, please. So what's an angle? When you measure an angle, you need to identify a vertex. So here, as you can see, step one is vertex is O. And the step two for measuring an angle, place the center of the protractor on the vertex. Okay, what's step three? Align the protractor's baseline along OY and note the degree. This is exactly what's taking place. Next slide. Types of angles. There's an acute angle, which is less than 90, an right angle equal to 90, an obtuse angle greater than 90 and less than 180, a straight angle 180, a reflex angle greater than 180 and less than 360, and then a complete angle equal to 360. Right angle to the right here, the angle that exactly measures 90 degrees is a right angle. So when we hear and talk about sextant and take your 90, minus from 90, subtract from 90, it has to be a right angle because it's got the 90. Okay, it's pretty obvious. It is also considered as half a straight angle, as half of 180 makes a right angle. Next slide. A sextant is an extremely precise protractor used to measure the angle between the horizon and the heavenly body. So as you can see, if Adam points up to that star, that's at 90, and then the horizon, there's your right angle. It's just very simple. Next slide. What does a sextant measure? A sextant is a navigational instrument used to measure angles. In celestial navigation, it measures the angle between the horizon and the celestial body, star or a planet. Used horizontally, it can measure the angle between two terrestrial objects, say a lighthouse, spire, or a pier. Next slide, please. A sextant is a navigational tool that measures elevation using angular distances. You can use a sextant to determine the altitude in the sky of the sun, moon, or other celestial bodies relative to the horizon. As you can see here in the picture, the observer is right there where the vertex would be. So he's got a GP. And then the star is over there, and it's got a GP directly over there somewhere. And there's your horizon line, the green. And it's an elevation angle. And it only works with a flat baseline. Next. Zenith distance. This is key because the sextant doesn't measure zenith distance. It's a complement of the first measurement, the angle. Zenith distance of a body is the angular distance from the observer's zenith. So you see, it's the angular distance from your zenith. It's the complement of the body's altitude. When the altitude is found by measurement with the sextant, the corresponding measured zenith distance becomes available. As you can see there with the blue dotted line. That is the radius from the GP of the sun or star to you. That is in nautical miles. Next slide. Altitude, height observed, is the observed height of the star or sun and how co-altitude, 90 degrees minus height observed, the elevation angle, is the complement of the measured altitude, also known as the zenith distance. Co-altitude equals 90 degrees minus the observed height of the sighted star. Whenever you hear them squeal when we say 90, this is why. So now you've got the first part already measured. Now I'm just highlighting this, the second part, the complement, the angle, the co-altitude, the zenith distance. Next. Altitude or elevation, the angle the object makes with the horizon. Objects that seem to touch the horizon have an altitude of 0 degrees, while those straight above you are 90 degrees. The zenith distance is 90 degrees minus the body's altitude above the horizon, the complement of the altitude, and hence is also known as co-altitude. I took the liberty to take another image where they have 3 circles of equal altitudes, and each of them would be different radiuses from the GP of the star 1, star 2, star 3 to the observer. But it's pretty obvious that when I do that drawing of the complement, the zenith angle, the distance with the dotted line, that is what you're looking for after you get the elevation angle. This is how it works, folks. This is all from their books, by the way. All these quotes and everything is from their books. Next, please. Well, what about Alt-Az coordinate system? This is a local coordinate system to use for locating objects in the sky as seen from a point on the Earth's surface. Key point. Azimuth is the angle of the celestial object around the sky from north. It measures along the horizon from north, 0 degrees, through east, 90 degrees, south, 180 degrees, west, 270, and back to north. So if you look at the image to the right, north would be starting 0 because it can also be 360. And then to the right would be 90. And then straight down from north would be south, 180. And so you know that GP of that sun, the bearing would be something past 180 and before 270. So we can guess and say it's 205. But it's in the book once you do it. So that's how you get your bearing to the GP. Next slide. This is interesting. This came from one of their sites. A guy took a paper plate and decided to show it in a simpler fashion, I guess wanting to communicate to younger minds, but it's the same thing. Right angle. An angle that measures exactly 90 degrees is called a right angle. It is formed when two sides of an angle are perpendicular to each other. They don't like that word either, perpendicular. So as you can see on the paper plate, you've got a sailboat. Directly above would be the zenith of the navigator holding the sextant. So there's your 90, but you can't get a 90 unless you have a flat baseline to be perpendicular. So there's your 90 degree. And then you measure the altitude of the star, the red, and then the co-altitude, the zenith distance, would be the difference. If you go to the right, it's the same thing. Height is elevation angle measured from horizon. Zenith angle measured from vertical. You can see it's matching everything I've shown so far. And then A equals azimuth angle measured clockwise from north. So you get your bearing, your direction. Next slide. Let's suppose you just used your sextant to determine that the angle between your celestial body and the horizon is 30 degrees. So your elevation angle is 30 degrees in this case, as seen in the picture below. From the rule of right triangles. Now, I'm going to read that again. From the rule of right triangles, we know that the angle between a line extending up from your position and the celestial body is 60 degrees. Well, how do we know that? Well, 90 minus 30 equals 60. Pretty simple. You can see an interesting relationship between this angle in the air. You know those arc minutes and all that, nautical miles? Comes from the angle in the air. You just measured the angle between your ground position, back to the ground, and the celestial GP. In essence, you just measured how many degrees of arc lie between you and the celestial GP traveling on the surface of the Earth. Not the center of the Earth, the surface of the Earth. What does 60 degrees of arc between you and the celestial GP mean? If you remember the old rule that 1 minute of arc equals 1 nautical mile, you have your answer. Your distance from the celestial GP is 3,600 nautical miles. How do we know that? Well, you minus 30 from 90 gives you 60. 60 times 60 nautical miles, 3,600 nautical miles. You are now entitled to draw a circle of position, a radius, 3,600 nautical miles around your celestial body, and be reasonably sure that you are somewhere on it. Stephen M. Kastner, PhD, is a researcher for NASA and author of 2 books. Next slide, please. Right angle, circle of equal altitude, a circle on the Earth that is the focus of all points equidistant from the substellar point of a celestial body. Another point, the GP. The altitude of a celestial body is measured from any point on that circle is the same, also called circle of position. So as you can see here on that one image, the navigator somewhere on that circle, they just don't know where they are until they do a second or a third. And to the right, we use the same illustration from their books showing a pole and how you can measure 60 degrees and it's equidistant anywhere on that circle. Next slide. So what is a circle of equal altitude? Back to that other slide. Well, if you sight one star, you're not really triangulating, but you know you're somewhere on that circle. But when you get the second star and third star, you can triangulate. And this is what it's showing here. And notice they got the box designating right angles. This is from Baller site, not Flat Earth Sextant sites. This is their drawing. This is what they're telling you is happening. And then we know what the zenith distance is the complement of each of those altitude measurements. Next. It looks like this. So if you shot two stars, you'd have the subpoint or the GP of the moon and the sun right there. And where the cross is where you are. Now, you know that you took off from Spain and you're somewhere near the coast of Morocco. So it wouldn't be the one in Brazil because of your dead reckoning the day before. So now you know exactly where you are in relationship to everything. Next. The big lie. This is the big lie for all those people who like to look at pictures and say, see, it shows it working on the globe. Well, no, not really. So as you can see here, and Adam, if you can take the cursor to the center of this globe model, you can see that's half of this protractor. And notice the plane. That's a flat baseline there all the way to the equator line, which, by the way, even on their model is 0 degrees. So you got your baseline 0 degrees all the way to 90. You can't get a more maximum altitude or elevation angle than 90. So it's a right angle. I don't know why they're afraid of right angles. Oh, I know, because it's a big lie. It doesn't emanate from the center of the Earth. It comes from the surface. In celestial navigation, we know that the sum of the angle and its complement is equal to 90 degrees. They form the right angle together. Next slide. This is what's happening. Everything, I'll give credit where credit's due. Nathan Oakley said everything below that horizon line is a lie. They first measure it flat. Then they draw pictures to show you that, look, this is where we're getting it from. It's not happening, folks. Any evidence you can have a curved adjacent while acquiring an elevation angle? It's impossible. Next slide. Well, bye-bye ball, right? The black swan, because if they were going to prove a sphere, they could easily do it. But in this picture from BLMSB 69, he's at a 1 foot observer height, and according to 3959 radius, guess what? The limitation of that geometric horizon, the thing that blocks boats and buildings, you know, the bottom first, has to be 1.22 miles. And yet we see platform Hill House at 6.21 miles. We see platform Habitat at 9.41 miles. And clearly the horizon is beyond that. So Earth curve is not where Earth curve should be, which means Earth is not curving. You follow? Next slide. Shout out to QE, who put together the Molus Tollens. It's going to leave a mark, and it has. That's where the Sextant was born. If P, then Q. Not Q, therefore not P. If the Earth is a sphere with a radius of 3959 miles, we're begging the question for you, ballers. If it is, then every horizon distance measurement must be no more than 1.225 times the square root of the observer's height in feet, Q, based on your curve calculators. Not Q, horizon distance is greater than 9.41 miles, therefore not P. Earth is not a sphere. Next slide. The height of the sun or of any star in the sky is called its altitude. And so the altitude is always an angle to be measured in degrees and minutes. The point directly overhead is the zenith. The angle between lines drawn to the horizon and the zenith is 90 degrees, or a right angle. Navigation, Harold Jacobi, professor of astronomy. Last slide. Any evidence you can have a curved adjacent while acquiring an elevation angle? Nathan, what do you think?
I think it's an excellent presentation. Very well done. So although I said it in the build-up to the presentation, that's the accumulation of lots and lots of information followed by lots of traps being laid out for ballers to give us their absolute annihilation of their own claim. And be welcome to Flat Earth as a result, because to answer the question, any evidence you can have a curved adjacent whilst acquiring an elevation angle? No. It defies the trig. This is what you need. This is what you use, and this is how it's done. This, on the right-hand side, isn't. It's absolutely absurd. You've only got to look at it to know it's absolutely ludicrous. No, you can't have a curved adjacent. It's got to be straight for it to be a triangle with a right angle. Excellent work, 10th man.
Just to really reiterate, but I mean, may have been missed, but this is really quite interesting, this, but the alt-as coordinate system, this is key to it as well. And this is very different to the celestial placing. This is how the grid system for you. And just what I wanted to point out how this grid system's defined, look, is we take the observer, we take magnetic north as our first reference point, and then on a flat plane, we designate our bearing. That's what the azimuth angle is. But again, you can see that's playing out on a flat plane to go up to then get your zeniths, get your elevation angles. But again, it's another visual representation of the maths and what it's doing there. That this, even the azimuth angle, what we see, is applied onto a flat planar surface. It's not teetering on the top of that ball, that azimuth angle.
And I'll stress what I stressed at the beginning of the presentation from 10th Man, which is to say that this is a flat earth proof. You and us, that would be, let's include the third group, anti-flat earthers, flat earthers, and globers all require this to be done on a flat plane. Now, if you happen to come into this discussion about sextants with a fundamentalist religious belief that the Earth is a sphere, then you're going to be correcting that. Now, you've bastardised something we call height of eye correction, otherwise known as dip correction, and have turned it into something it isn't, which is to say a correction for you from your fundy sphere belief geometric horizon we debunked, and you told us you haven't got a straight line to anymore for 2 straight years, to a flat plane. So even if you come here with a fundy sphere belief, you're going to be correcting that flat before we move any further. Now, this is a lot to take in for a lot of you on the anti-flat earth side, I know. Doesn't change the fact that you're going to be correcting your sphere belief.